Hello, all you awesome mathematicians, and welcome back to another lesson. Today is lesson 1.5, which is on the Pythagorean Theorem. Our objective for today is I can use the Pythagorean Theorem to identify problems and to solve them. So today's lesson is broken up into three parts. First, we're going to talk about how to identify right triangles and to identify if we're going to use Pythagorean Theorem on them or not. Then we're going to talk about how to use the Pythagorean theorem to solve these problems. And finally, we'll look at how to simplify radicals, which is something we'll need to do if we end up getting an answer that is not a whole number, like a decimal. We'll look at how to simplify those radicals. So let's start with the Pythagorean theorem itself. We have a squared plus b squared equals c squared. So what I'm going to do is I'm going to highlight our A, B, and C. I'll highlight our A in red, our B in blue, and our C in green. So these three letters also represent the sides of a right triangle. The C represents the hypotenuse of a right triangle. So here, underneath the C, I will write hypotenuse. And the hypotenuse is defined as the longest side on a right triangle. But a better way to find the hypotenuse, because sometimes it's hard to tell which one really is the longer side. So the best way to tell which one is the hypotenuse is whichever side is across from the right angle. Because remember, if this is a right triangle, it needs to have a right angle, right? So across from that right angle, I'm always going to be able to find the hypotenuse. If I look here at the triangle, I see my right angle here, and I know it's a right angle because it's a little square. And remember, right angles are 90 degrees. So if I have this right angle here, how can I tell which side is across from it? Simple. I'm going to draw an arrow starting from this point and going across, literally across the triangle. And that arrow will always point at the hypotenuse. So we know this will be our C. A and B represent the legs of our right triangle. The legs are connected to that right angle. Now sometimes we'll have legs that are the same length, but usually these legs will be different lengths. And so we'll call A the short leg. So A will represent the short leg. I can highlight that side in red. And we'll use B to represent the long leg. Now don't get this confused. I said that the hypotenuse is the longest side, right? But out of the two legs of the triangle, B is going to be the long leg. Now A and B, they can be switched around, honestly, and it won't really change much of what you're trying to solve for. So you can switch A and B around and you'll still get the right answer. The only one that can never switch anywhere is C. C is always the hypotenuse no matter what. I can't let any other leg be the hypotenuse. C always has to be that longest side, that hypotenuse, that side across from 90 degrees. Now that we have identified the triangle, let's look at the formula itself. Let's look at the Pythagorean theorem. And all it says is a squared plus b squared equals c squared. Remember that these squares, they don't mean times 2. They mean this number times itself. So this is a times a plus b times b equals c times c. So that's what that square represents, and that's our Pythagorean theorem. So now that we have identified it, let's look at how we can use it to solve problems. Here, I have a triangle, and the first thing that I want to do is figure out what am I looking for? What am I doing with this? So I am looking for the missing leg. This side that has no length, I want to find that. Okay, so now that I know that, is it a right triangle? Can I use Pythagorean theorem on it? Well, let's see if we have that right angle, and we do, right? Here is our right angle. So now that we know it's a right triangle, okay, so can I still use Pythagorean theorem on it? If I have two sides given, if I have those two sides, or any two sides, then I can use Pythagorean theorem to find the third side. However, if I was missing one of these sides, I can't use Pythagorean theorem anymore. But in this case, we do have two sides, so we can use Pythagorean theorem here. Okay, so the next step is to figure out where is my A, my B, and my C. So I'm always going to start by drawing an arrow from the right angle to the side across from it. I go across the triangle, and that shows me which side my C is. Now for A and B, remember, it really doesn't matter. I can let this be A, this one up here, and this one be B. But just to stay consistent, we want to try to keep A and B with the shorter leg, A being A, and the longer leg being B. So since 15 is smaller than 20, I'll let 15 be A, and 20 will be B. So that way A is the shorter leg, B is the longer one. Cool. So now I have everything labeled, and I know I'm looking for C. So let's write out our Pythagorean theorem. And I like to write out the formula every time I'm going to use it, just so that I have it in front of me and I know exactly where each number is going to go. So a squared, we know a is 15. So I'll put 15 instead of a. I'm going to substitute. And then 15 squared. Don't forget to bring that square back in. Now b squared, b is 20. So I'll replace b with 20, and I'll put square there, equals c squared. Now, since I don't know c, I'm going to leave that as c squared. So now that I have my Pythagorean theorem put together, the first thing I'm going to do is find out what 15 squared and what 20 squared is. Now, if you're not sure, that's okay, but I'm going to recommend you to go to the calculator at Desmos.com. Use the calculators they have there to help you. I know that since we're not in school, we can't really use the Nspires, right? And I can't mail them out to you or anything like that. So use the calculators in Desmos. Trust me, they're really, 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 really good. But luckily, I know what these numbers give me. 15 squared is going to be 225. And 20 squared is going to be 400. And that still equals c squared. So now I'm going to add these two together. So 225 plus 400 gives me 625. That's going to be c squared, equals c squared. Now, at this point, there doesn't look like there's much else I can do, right? I'm kind of stuck here. Because, look, I'm going to do this in a different color. I have c. That's what I'm looking for. But over here, I have c squared. So now it's like, well, what am I going to do to get rid of that square part? And I'll show you what you're going to do. You're going to use something called the square root. The square root is this symbol. It kind of looks like a divide, right? Something like that. But notice that it has this little extra thing going on here, that's the difference there. So be careful with that. We have the square root of c squared. And then we'll take the square root of the other side too. I'm taking the square root of c squared because the square root and the square are opposites of each other. And remember from Algebra 1 that when I use opposite in equation, it's going to help me cancel stuff out, right? So here I'm canceling out the square by doing the opposite of the square and taking the square root. So what that's going to do is it's going to get rid of the square part and leave me with just c. Now on the other side, I need to plug this into the calculator, square root of 625, to figure out what that gives me. But I already know what it is, and it's going to be 25. And so now that I have c and just c, I have my answer. Let's take a look at another example here. This time I have another triangle, and you'll see I have 26 given, and I have 10 over here given. So just like last time, I'm going to start by identifying if this is a right triangle. And I see the right angle here, so I know that it is. Okay, so I know it's a right triangle. There's one side missing that I need to find, so I know I'm going to use Pythagorean Theorem here. So I'm going to start by finding my c. Always start by finding the c. It's the easiest side to identify. So let's start with that. I have my right angle here. I'm going to draw my arrow across the triangle, and it points to this side over here with the 26. So this side must be c. Now between the two legs that this triangle has, 10 looks like the shortest one. So I'm going to put A for 10. And for the longer leg, I'll put B. So notice that this time, what I'm missing is the B value here. So it's going to be a little bit different to calculate this. So let's take a look at what we'll do. I'm still going to start off by writing out my Pythagorean theorem. A squared plus B squared equals C squared. I'm going to substitute in my numbers. A is 10. So I have 10 squared. B is unknown. I don't know what B is. So I'll leave that as B. And then C is 26. So I have 26 squared. Now I need to figure out what these square numbers are. So I'm going to find out 10 squared, 10 times 10, which is 100. Then I have B squared. I'm going to leave that alone. And then I have 26 squared, which gives me 676. Now at this point, we know that it's different than the last problem, right? Because we had the C on this side, so we just added these two together. But I can't do that this time, because since I don't know what B is, I can't add 100 plus B squared. I don't know what B is. So what I need to do is a little bit of algebra here. Because see, I'm trying to solve for B, right? I'm trying to solve for B squared for B. So I need to get that B by itself. Right now, it's not by itself. On the left-hand side, I have B squared, but I also have the 100. So how do I get rid of this 100 to get B squared by itself? Well, if you remember from algebra, opposite operations, inverse operations, I can use those to cancel out things that I want to get rid of. So if this is positive 100 here, I can use negative 100 to cancel that out, So I'm going to cancel this out. But since this is an equation, I need to make sure that whatever I do on one side, I do to the other. So on the other side, I'm also going to subtract 100. And that gives me 576. On the right-hand side, on the left-hand side, I drop the B squared down. And so I end up with just B squared. And just like last time, I need to take the square root of both sides to find what B is. So here I end up with B. And the square root of 576 ends up being 24. So my answer here is 24. Now, I would encourage you to study the process that we're using here, because knowing how to manipulate the Pythagorean theorem is very important. It helps your algebra skills, it helps you understand how it works. But I am going to show you two little shortcuts that you can use. There are two little shortcuts, two rules that we can use for Pythagorean theorem. If you know that C is missing, we can turn that equation, that Pythagorean theorem a little bit, we can manipulate it, and we can use this to solve for C directly. Notice that the only thing I did when I rewrote this equation was, instead of C squared, I just have C now. But on the other side, I have the square root of A squared plus B squared, which makes sense, because if I'm getting rid of this square, it means that I took the square root of this side, right? So that's all I'm doing here. And it's a little effective shortcut. If you happen to memorize this, awesome, because this is how we find the value of C if we don't know what C is and we're given A and B. Now, if A or B is missing, let's say that A is missing. So I want to know how to find the value of A. So if I rewrite my Pythagorean theorem a little bit, I end up getting the square root of C squared minus B squared. Now, what if I want to find B? Well, A and B simply switch places. So B equals square root of C squared minus A squared. So these are some very calculator-friendly formulas that you can plug the numbers straight in, plug that into the calculator, and get an answer from that. Let's continue on, and let's take a look at what happens if I end up with an answer that doesn't come out as a clean number. So in the previous two examples, I got 24 and I got 25 here. Those are very, very clean, very nice looking whole numbers, right? So there's not a lot to worry about there. But let's say, for example, if you do the Pythagorean theorem and you end up getting this square root of 72. Well, if I take the square root of 72, I end up getting approximately 8.48528137 la 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 la. That's ugly. That's nasty, and I don't want to see that. I would rather prefer being mathematicians, right? We would prefer nice, clean, exact numbers, not really so much these decimals here. So what we're going to learn in this section is how to simplify a radical. And what I mean by radical is this thing right here. Anything that has a square root, a number with a square root, is called a radical. So the radical, it would be like the entire object. The square root is the operator, but the radical would be the whole package. So to simplify this, simplify means I'm going to try to get the number inside the radical to be as small as it can be. To do this, we need to remember what prime factorization means. Sorry guys, I forgot how to spell. So prime factorization means if I factor a number, I'm trying to get as far down as I can. And what I mean by as far down is I'm breaking this number apart into its factors until I can't find any more factors. So as a quick example, let's say, for example, 12. If I want to do the prime factorization of 12, then I'm going to start factoring. I want to look for two numbers that multiply to give me 12. I know off the top of my head, 6 times 2, right? Now 2 can be broken up into 2 times 1. But I don't need to show this part because look at what happens. This can be broken into 2 times 1, then this, 2 times 1, then this. Like, it's unnecessary at that point because it's just going to keep repeating, right? So I have my prime number here. There's no other factors for 2 besides 2 and itself. So once I have the prime number, then I can stop the factorization. However, the 6 is not a prime number because 6 can still be broken into other factors other than 1. I know that 2 times 3 gives me 6. But we already established that 2 is a prime number, so this side can stop there. Is 3 a prime number? Is there anything else that I can multiply to get me 3 besides 3 times 1? No, there isn't, right? So this is as far as I can go. This is the prime factorization. Now let's apply that to the radical and see what we would have to do here. So I'm going to start factoring 72. And I'm going to start with 2. I'm always going to start with the smallest number that I can, which will usually be 2 or 3 or 5 probably, or 7. If you think of your prime numbers, those are the numbers you're going to try first. And so 72, what number do I multiply by 2 to get 72? I can just divide it, right? 72 divided by 2 is 36. So I know that on this side, I must have 36. Now I'm going to do the same thing with 36. I'm going to divide 36 by 2, not 3. I don't know why I wrote 3. But I'm going to divide that by 2 to find the factor of 36, which ends up being 18. Now I'm going to do the same thing with 18. I'm going to factor it 2 times 9, right? And 9 is not divisible by 2, but it is divisible by 3, right? In fact, 3 times 3 gives me 9. Cool. So we've got our prime factorization done. This is as far as we can go, right? So how do we apply this to simplify the radical? Well, this is what we're going to do next. We need to identify pairs of numbers. So the pair of prime numbers that we see. So for example, a pair of 2's are here, and I'm going to circle those. I look for another pair of 2's and I don't have it. But I do have a pair of 3's here at the very bottom. I'm going to circle those. And so what happens is I have a pair of 2's and I have a pair of 3's and I have a 2 by itself. So when we want to simplify our radical, I'm going to redraw our square root symbol, our radical. The number that goes inside is any numbers that were left out that don't have a pair, any of the prime numbers. So for example, this 2 right here was all by itself. And actually, let me redraw this because I'm going to need more space on the left-hand side. Let's put it over here. So again, any numbers, any prime numbers that were left by themselves are going to go inside the radical. So by itself. The numbers that were circled that had pairs, I'm going to put those in the front of the radical. So here I have the 2 from here. Now I'm not putting both of the 2's. I'm only pulling one. So the other one just kind of disappears and I bring one of them out. I do the same thing with the 3's down here. I let one of them go and the other one, I'm going to put it over here in front. Now if you look at this, it looks like it's 32. It's not. This is 3 times 2. So any additional numbers that end up being either in the front or on the inside get multiplied. So here I'm going to multiply. So 3 times 2 gives me 6. And I'm going to write that in here. And then I have square root of 2. And that, my friends, is how you simplify a radical. So 6 square root of 2 is exactly the same as the square root of 72. But like we said, we want to simplify it. So we made the inside number of the radical as small as we can, and we bring out the biggest number that we can from the inside. We do this by prime factorization. So if you need a repeat, please rewind the video or reach out to me if you need some help, or to any other teacher, whichever teacher you have. So that's it for this lesson, guys. I hope it helped you out. Remember, please let me know if these are helping you out or if there's something you guys want me to do differently. I am open to feedback. I'm open to criticism. So please let me know. So I hope you got something out of this. I'll see you guys in class. Take care, and I'll see you guys next time.